today's presentation, I'm going to be talking about the buzzer and a motion detector sensors. The buzzer and the motion detector sensor is part of our layer 3 architecture. Now I've made a mark on the items of layer 2 that we are going to be using for our programming. That would be the I/O ports, timer counters, interrupts. Now the reason I put the buzzer and the motion detector together is because I intend to write programs where the motion detector detects some motion and then the buzzer provides an alarm. So agenda for today. First I'm going to talk about the motion detection, then I'll address the buzzer, and we'll have three sample programs. The first sample program, we're going to use the motion detection with a very simple buzzer. Next, we are going to sample program 2 is going to address how we can come out with more sophisticated buzzer sound. And finally, sample program 3 will use the motion detection with a more sophisticated buzzer sounds. So let's start by talking about the motion detection. So we're going to use what's called a passive infrared sensor, which is a PIR. Now this sensor is one of the most commonly used motion detectors. All objects, as you probably know, emit some level of heat in the form of infrared radiation. Inside our PIR sensor, there are two pyroelectric sensors that can detect changes in infrared radiations. So the way this works is as follows. The sensors first establish a baseline level of infrared radiation in its environment when there is no movement. So you turn it on and a baseline infrared level is set up by the sensor. Next, when a warm object like a person or an animal moves into the sensor's fields of view, the pyroelectric sensor detects a high level of infrared radiation. Once motion is detected, the sensor sends a signal to the microcontroller. So let's see how this works. So the infrared sensor, when you turn it on, defines its environment. Next, if the environment changes, for example, the person coming in that adds heat radiation to the environment, the sensor immediately sends you a signal, meaning that somebody has entered your area. Now the characteristics of the sensors is it typically detects motion within 5 to 12 meters, covers wide rate angle between 90 and 180. And another advantage, it does not emit any energy. It only senses infrared radiation. So that's an advantage because nobody's going to know that you have this sensor because it's not irradiating any signals. So let's talk about the buzzer. So this picture shows a typical buzzer, and this is the internal of the buzzer. And I think the important thing to understand from here that there is a diagram, and the diagram will be start vibrating once a signal is provided from the microcontroller, and that's going to generate sound. So inside the buzzer there is a small piezoelectronic element. When an element signal passes, I should say, when an electrical signal passes through it, it causes the element to vibrate back and forth. This vibration creates sound. The microcontroller needs to transmit to the buzzer a square signal wave or a PWM signal to generate sound. So either you send it a square wave by turning your output to on and off, or you can use the pulse width modulation. In our first sample, we're going to use sending a square wave, and then the follow-up samples, we're going to see how we use the pulse width modulation. The frequency of electronic signal determines the pitch. Higher frequency, higher pitch sound. Lower frequency, lower pitch sound. So let's go to our first sample program. So we have a motion detector hooked up to our microcontroller PD2 port, which is the interrupt 0. Next we have a buzzer hooked up to the PB1 port, which is one of our pulse width modulation capable ports. And then finally we have an LED hooked up to PC0 port. Now this is an LED that when you turn on, it puts out different colors. So let's see sample program 1. Each time the motion sensor is detects motions, the output goes high. If motion is detected, then turn on the buzzer and actuate the color LED. So if we capture a change, because means that there has been some motion detected, then we're going to fire up our buzzer, and turn on an LED. Use aim to capture capabilities to detect the signal coming from the motion sensors. Drive the buzzer using a loop with 100 milliseconds delay. So let's see our first program. I'll start by giving you a global view of the program. First, we have a routine to initialize the ports. We have a routine to initialize interrupts. We have a routine to enable the interrupts. Then we have the main program. And finally, we have our interrupt service routine, which is where everything is going to be done. We're going to turn on LEDs, we're going to drive the buzzer, and then we're going to turn off LEDs. So let's get into the details. So let's start by looking at the init ports. So what we do with this statement is we enable the port B to be output, so we can turn on LEDs. Next, we enable the port C to be output also, so we can drive the buzzer. And then finally, we enable the port D to be input. And that's we're going to get a signal when there is motion detection. And then we also implement a pull-up resistor, so we know the state of that port at all times. So let's go and look at the init interrupts. So what we're going to do here is we're going to enable our interrupt to trigger with a rising edge to detect any incoming signal. The port we're going to use is going to be int 0. So this is going to take care of the input capturing. Next, we have a routine which is going to enable the global interrupts. Now, continue with the main program. What we have is, what this program is going to do, I should say, is going to call out all the routines needed to initialize and enable interrupts. That would be init ports, init interrupts, enable interrupts. So let's jump into the interrupt service routine. This routine is going to be triggered every time there is an input to the microcontroller. The input that would be captured by the input capturing capability. So once we know, if we are in this interrupt service routine, we know that the motion has been detected. So the first thing we do here is we turn on the LED. Next, we're going to drive the buzzer by turning on and off port C every 100 milliseconds. And that's going to give us a particular tone that we're looking for. We're going to do that 10 times. Next, we're going to leave the LED on for another 2 seconds. And finally, we'll turn off the LED. So to recap, what we do is we capture an input, and that input triggers a interrupt, and the interrupt drives the buzzer to generate an alarm, and it turns on and off a particular LED. So you have a sound and a visual notice that there has been an incursion into your area. Now this is the sound generated by the alarm using the loop with 100 milliseconds delay. Okay, so that you get an idea what the scene sounds like. So let's go to our second sample program. In this case, we're going to use our microcontroller hooked up to the motion sensor, and we're going to generate different sounds. So we learned how to use the buzzer. So create a program that will play music notes using the buzzer. Use pulse width modulation microcontroller capability to generate and transmit the following frequency signals. So these are frequency signals for the notes. That's do, re, mi, fa, sol, la, si, do. Okay. So let's see how we program this. So there are certain things that we have to remember. So I noted first that the frequency is going to drive the pitch. So how do we control the frequency using pulse width modulations? So this is our timer. Starts from 0 and goes to max value. This is number of ticks, and this is time. Now this max value is the ICR1 register. The max value, which determines the amplitude of the signal, is 1 over frequency. So this is what we're interested in generating. That's going to be, we want to generate this frequency, so then we know what's going to be our ICR1 value for our register. Now the frequency of electrical signal determines the pitch, like I noted. So we have high frequency, high pitch, low frequency, low pitch. So let's continue to put together our picture. So now, like I noted, the ICR1 is going to define the period. And the period is going to be 1 over the period is going to give us our frequency. So as I decrease the ICR1, I'm going to get a smaller period, and that's going to change the frequency. As I increase the ICR1, also the period increases, and that creates a increase in pitch. So now, as we generate the wave, we need to set up the duty cycle. In this case, we're going to use a duty cycle of 50%. So that means that this point, which is 50%, is going to be 1/2 of the ICR1 register. So our duty cycle, 1/2 of the ICR value. Now, what we want is once the signal gets to its max value, then it goes down, sets onto the bottom again. So it goes up and down. So to accomplish this particular thing that we want here, changing the ICR1, and then once you get to the point, then start over in the period 50%, we need to use a non-inverting, a compare output mode for non-inverting. And we've done this before. The main concept here is that we need to understand that this max value is related to the period, and that's related to frequency. So let's, this is the frequencies we want to generate. And this is a little description saying they are nodes. So let's put together all the math that we have to do to make this happen. So first, as usually, we show that our controller clock is 16 megahertz. That means 16 million ticks per second. And then also I'm noting that we have a 16-bit timer, which means that the maximum count is going to be 65,536. And finally, I'm saying, hey, we need to be, this is the range that we have to accommodate, that they have to fit within the 16-bit timer, or we have to set up a scaler. So let's do some of the calculation. So the minimum value, the amplitude would be 1 over the frequency, and that's in seconds. But we really want to know the ticks, so we multiply it by the number of ticks per second of our clock, and the value is would be 61,155.0663 ticks. So no prescaler is needed, but we'll use an 8 to provide a little bit of margin. Because we have a 65,000, we're 61,000, let's just give us some margin. Now the max value, which is 523, and that the amplitude would be 1 over 526. Then again, we figure out what are the number of ticks by multiplying the number of the amplitude in seconds times the ticks per second. And the result is 30,578 ticks, so no prescaler is needed. However, we're going to use an 8 because that's what we decided before. So now, if you look at your specification, the 328 datasheet, they have this formula, which is the frequency for the pulse width modulation is equal to the processor clock divided by the scalar multiplying 1 plus stop. Now let's see what each parameter means. So that's the, like I noticed, the pulse width output frequency. This is our clock, prescaler, the N, and the top is the desired amplitude, which is ICR1. So when we want this frequency, what we're going to have to figure out is, given this frequency, I should say, we need to figure out the ICR1 so we can send our pulse width modulation signal. So what do we do here? So what I do is, yes, I want to know what's the top. So I just get this equation, turn it around, and put the top is equal to the microprocessor clock divided by the pulse width modulation signal times the scalar, and everything subtracted from 1. So that's output pulse width modulation, our clock, prescaler, and this is the top that we have to use. So we know that the pulse width modulation that we want is going to be the frequency, based on the frequency we're going to be used. So let's look at the sample program, see how we got that accomplished. So I'll start by giving you a global view of the program. So we have here routine timer 1 int, where we're going to do all the tasks associated for initializing the timer 1. Next, we have a routine called play tone, and what we're going to do there is we're going to calculate all the parameters needed to get the correct frequency and play that tune. Next, we have the stop tune, which is after a certain amount of time, we'll stop to play that note, or tune, I should say. Next, we have the main program, where we're going to call out whatever routine needs to be called out to play the required tunes. So let's get into the detail. So timer 1 init. So first line of code, we're going to set up the timer to be an output. So that gives us the capability of putting out a PWM signal through this port. Next, we're going to set up our PWM signal, and as I noted before, it's going to be non-inverting mode. And finally, for this routine, I'm setting up the scalar of 8. So let's go to play tune. The input for this routine is going to be the desired frequency, desired prescaler, and then how long we want that tune to be played. So I start by an if statement where I say if the frequency is 0, don't do any of this stuff. And the reason is because inside the guts of this routine, I have the frequency is a multiplier, and then it divides, and if you allow a 0, you end up 1/0 division, which is not allowed. So we assume, let's assume that the input was not 0. So this line, what it does is it calculates the frequency, the desired frequency. So we do that utilizing the formula that I already explained. So that's our microcontroller clock speed divided by the prescaler multiplied by this desired frequency, and this whole result subtract 1 from it. And the ICR1, which is the top value, this is where I assign the top value to the ICR1. Next, I have the parameter for setting up the duty cycle. As I noted, we are going to have a 50% duty cycle, which means that we have to set up we have to divide the top value by 2, and that's what we assign our OCR1 parameter. So with these two parameters, we have the signals pulse width modulation going to the buzzer. Now we have to figure out how long we're going to do that for. So we got a requirement, a particular duration. So what we do, we have a while which says duration minus minus. So it's going to decrement one value, a unit each time it goes around. So what we have inside is a delay of 1 millisecond. So every time it goes around, it uses 1 millisecond and keeps decrementing the required value by 1 until it gets to 0. Once it gets to 0, then it gets out of the while loop and we have the stop tone. It goes to a stop tone, which is right here. And what this routine does, it sets up the ICR1, which is the tap, to 0. That stops the tone. So finally, let's talk about the main program. So the first thing it does is initialize the timer, which is the only thing we really need to initialize here. And then it calls the play tune routine. And as I noted, the first parameter is the desired frequency, the scalar, which in this case is 8, and then duration, which in this case is going to be 500 milliseconds. So it goes through each of the tones. Now this, if you look at these tunes, this is do, re, mi, fa, sol, la, si, and do. Those, if you play this, send these frequencies to the buzzer, that's what you're going to get. And finally, we wait 1000 milliseconds, and then we go into the infinite loop. So, recapping, what this routine does is you put in an input of the frequency, the scalar, and the time you want to play in that note or that tune, and it does exactly that. So let's go to the next sample program. So before we go to the next sample program, let's listen to the output of this program. Okay, so let's go to our next sample program. So in this case, it's going to be similar to the first sample program, except that when motion is detected, we're going to put a different tune here. So we have now control over to what output we want from the buzzer. So each time the motion sensor is detected, each time the motion sensor detects motion, the output goes high. If motion is detected, then turn on a buzzer and actuate the color LED. Use input capture capability to detect the signal coming from the motion sensor. So that's same as before. And finally, the new way of doing this is drive the buzzer using PWM capability at the following frequency: 261, 329 for 250 milliseconds. Wait 1 milliseconds of delay. And I put a little change in the program, so I did 261, 329, 321, 261, just to make it a little bit longer. So let's look at the code. So this program is a combination of the first two. So I'm just going to highlight the important items. So we need the ports, and as before, we enable the LED port for output, the buzzer for output. Now, one item that I added here was I set a port to be 0 for the buffer, and that's to ensure that the buffer is silenced during the power up. Next, we have the init interrupts, and that's same as before. We are just waiting for the motion sensor to transmit a signal. Next, as usual, we enable interrupts. Then we have timer 1, which is basically the non-inverting, and prescaler 8, taking care of the pulse width modulation transmission. Next, we have the play tunes, which it takes, as before I noted, the frequency, prescaler, and duration. And we just go through the formula and then leave the buzzer on as long as we were requested, during which is the duration. And then we stop the tune, which is just making the OCR1 to 0. So next, we have the main program. We initialize ports, init interrupts, enable interrupts, timer 1 initialization. And now I added something here. So I added up front, we play a tune, which is we make a little bit of noise, and then we turn on and off an LED. So basically, that's like a heartbeat. You turn on your microcontroller, and you get this feedback that is working. Otherwise, you don't know if it's working, and if the motion detector is not working, then you don't know where to start from. At least here, you know that you power up, and microprocessor inform you that, yeah, I've been power up. Next, let's go to the interrupt service routine. So here we turn on the LED, and then we play these tunes. These are tunes that I selected because they sound kind of like an alarm. So I did the 261, 329, 329, 629, and then I wait 1000 seconds, and after that I turn off the LED. So the big change here is that you can select what tunes you want to play once motion has been detected, and then so you have the visual, the light, and then you have a particular tune which is going to let the user know that there was somebody has entered a zone and the motion was detected. So now let me play the sound from this last program. Oops, sorry. Okay, so we finally got that one to work. So with this, we get to the end, to the summary. So in my presentation, I talked about motion detection sensor. I also explained a buzzer, showed how the simple way of using a buzzer, or how we can use pulse width modulation to get a better, nicer sound from the buzzer. So we have three programs, two dealing with motion detection and the buzzer, and one dealing with the buzzer, showing how to generate different types of sound. So anyhow, thank you very much for spending the time with me, and I hope to see you folks soon through this media. Thank you.